sounds of the jungle. You can't see through the dense vegetation, but you can hear sounds. You can infer the jungle's full of life. If you listened hard enough, I bet you could tell me where the animals are, maybe what kind of animals there are. Because you see, even though you can't see, you can use your other senses. You can use your ears to tell you about your surroundings. Now, today, astronomy has a single sense, sight. So, in other words, astronomy is deaf. Looking through incredibly powerful telescopes has revealed an incredibly wonderful and exciting universe. But the most exciting events in the cosmos are really hard to see, simply because they're really far away from us. So the most exciting events in the cosmos are thousands of millions of times the distance between the Earth and the Sun. So imagine that, 1,000 million times the distance from us to the Sun. That's enormous. So they're really difficult to see, these amazing events. But fortunately, astronomy will not remain deaf for long because of a single guy, Albert Einstein. Soon, his masterpiece, his theory of general relativity, will add a soundtrack to astronomy's pictures. Now, in a single year, 1905, Einstein shook the foundations of physics with 4 seminal papers. And if he could do this in a single year, imagine what he could do in 10. Between 1905 and 1915, Einstein worked tirelessly. And after this 10-year marathon that left him ill, actually, for several months to follow, he completed this masterpiece. He completed the theory of general relativity. This theory would eventually overthrow Isaac Newton's theory of gravity and replace it by something much more complicated but much more exciting. Now, one of the most striking features of general relativity, one of its properties is that it's a scientific theory in itself. And it is not just an opinion or my opinion that it's the best description we have today for how the universe works. You see, it's a fact, because unlike opinions and beliefs, scientific theorists must produce predictions, and these predictions must be testable and verifiable. Einstein's theory is no exception. His theory has passed all tests we have done simply with flying colors. Every single prediction general relativity has made has been matched with observations, at least until now. So, as I was saying a little bit earlier, one of the striking features is that Einstein gets rid of the gravitational force altogether. See, in Einstein's theory, Newton's apple does not fall from the tree because there's an invisible magical force that's pulling on the apple. In Einstein's world, the apple exists in a certain fabric of space and time. And this fabric of space and time is curved because of the presence of the Earth. So the apple falls simply because it's trying to follow a straight path in this curved space. I know. So I just completely contradicted what pretty much everyone learned in high school, right? Like, no gravitational force, what? So this was actually difficult for me to understand as well. So let me try to explain it in a different way. So most of you are probably familiar with trampolines, and maybe when you were young, there was a trampoline in your backyard. You loved to play on it, jumping up and down on it. Now, if you weren't jumping up and down, you would simply sink in the middle of the trampoline. And if your mother placed a baseball on the edge of the trampoline, the ball would simply roll down toward you. Now, what Einstein realized is that there's no invisible magical force that's pulling on the baseball. Rather, the ball rolls because it's on a curved surface, which in this case is being curved by you standing on it. So in Einstein's theory of general relativity, space and time form a mesh, a space-time fabric, just like the surface of the trampoline. And everything in the universe, you would agree, exists in space and time. So therefore, everything in the universe exists on space-time. And just like the surface of the trampoline can sink in when you stand on it, the fabric of space-time can curve in the presence of very massive objects, like stars, planets, black holes. So matter is telling geometry or space-time how to curve. And in Einstein's world, an astronaut is deflected by a star because the latter is curving the space-time geometry. Although it looks like the astronaut is being pulled by this star, the reality is that there is no force. The space-time geometry, its curvature, is telling matter how to move. So what do you think would happen if you started jumping up and down on the trampoline? Well, the surface of the trampoline would undulate, right? Just like waves are produced when you throw a rock in a pond. So can the surface or the space-time fabric undulate in the same way? Yes, it can and it does. That's one of the wonderful consequences of general relativity. Every time something violent happens in the universe, every time a star explodes, every time black holes collide, space-time undulates. These are gravitational waves. These are what I call Einstein's cries. These are the sounds of the universe. But they're not sounds in the usual way we think about sound. They're not vibrations in air. Rather, they're ripples in the space-time fabric itself. They're ripples in gravity. Because in Einstein's theory, space and time, this fabric I'm telling you about, is not rigid and absolute. It's relative and flexible. It can vibrate, it can oscillate, it can be stretched, contracted, just like the surface of a trampoline. So one of the most common sources of gravitational waves are black hole collisions. So let me show you a movie of two black holes colliding. Now, this movie was not made in Hollywood. This is a movie created by solving the full set of Einstein equations on clusters of supercomputers at national labs over many months. So you paid for these movies. Now, in this movie, we've painted the black holes gray and so that you can see them, essentially. And under them, you see a representation of the fabric of space-time. So observe how the black holes move around each other and how the space-time undulates as the black holes in spiral. Eventually, they merge, ending this dance macabre in a final gravitational scream of despair. And this is what I do. I solve the Einstein equations to calculate the gravitational waves that would be emitted, for example, when two black holes collide, and to try to understand what we can learn from them once we detect them. And you see, this is important because it's difficult to detect these gravitational waves in the first place if you don't know what to look for. Think about it this way. If you're trying to find a needle in a galactic haystack, it helps a lot to know what a needle looks like. Because if you know what a needle looks like, you can build a filter that filters out all the hay and keeps the needle. That's gravitational detection. And it's been quite a trip for me, literally. I mean, ever since I was a young child, growing up in Argentina, I knew I wanted to study black holes. That was my dream, right? So when I turned 19, I came to the US to continue my physics studies, to follow this dream. And today, I'm fortunate enough to be able to live this dream. Because you see, I get to wake up every morning and rush to work and be happy about rushing to work. Because I know that once I get there, I get to my office in the physics department, I get to sit down and study black holes and teach about black holes to other people and try to understand how the universe works and how we can learn more about it. Okay, but that's enough about me. What do you think gravitational waves would sound like if we could hear them? So in this next movie, I've created sounds from the gravitational waves that would be emitted if a small black hole spirals into a supermassive black hole. Hear the sounds, hear the chirping, hear the gravitational waves getting higher and higher in pitch. Yeah, it was timed and everything. Good. So you see there's richness, there's structure in these gravitational waves. And now I think you might be able to understand why we're so excited about these gravitational waves. Black holes are black, so you can't see them with telescopes. But there's rich information in the gravitational waves they emit when they spiral into each other, when they collide. Information about their sizes, information about their locations in the sky, information about Einstein's theory itself. And what's amazing is that these events are happening all the time in the universe. They're constantly going through the universe, through Earth. Right now, they're going through your own bodies. Can you feel your bodies undulating to the frequencies of the universe? Well, no, you can't, right? Because after all, these gravitational waves are extremely weak. To detect sounds, or gravitational waves in particular, you would have to build incredibly sensitive detectors. Now, the physics community has come together and, in a period of about 40 years, achieved that. They've built detectors. LIGO in Washington State, Louisiana, and soon in India, GEO in Germany, Virgo in Italy, and Kagra soon in Japan are advanced detectors. And we're almost ready to turn them on for the first time in a couple of years. So for the first time before the end of this decade, we will be able to detect gravitational waves. We will be able to confirm Einstein's last prediction. So told you about gravitational waves, and I told you a little bit about what we could learn from detecting gravitational waves, like their sizes and whatnot. But I left a very important part, the unexpected. Because you see, every time we astrophysicists look up in the sky with a new telescope that allows us access to a new frequency, or in a completely different way, with different particles that give us information, or in this case, with gravity itself, we're always delighted to find something completely new, something completely unexpected, something we didn't imagine, because our imaginations are limited, and astronomy, in this case, is deaf. So, to conclude, let me try to address one of the most difficult questions I've been asked so far, interestingly enough, by my own dad in Argentina. He would be like, Nico, what is all of this good for? So after 12 years of studying physics and gravitational waves, I still have trouble answering that question. And the reason is that it's often impossible to foresee the technological consequences of scientific discoveries. You see, especially fundamental and basic physics research. Well, when physicists discovered electricity and magnetism, they weren't trying to build a radio or a TV. When Einstein invented general relativity, he was not trying to build a global positioning system. But we use this technology all the time. GPS is in everyone's phone. It's a thing that allows you to find the nearest Starbucks or Thai restaurant in town. And GPS would just not work without Einstein's theory. So the failure to foresee technological applications is a failure in our imagination, not a failure in science. If anything, science and physics in particular are the primary drivers of innovation and technology, and as such, the primary driver of the economy itself. For example, thanks to NASA's effort to minimize the amount of weight carried by the shuttle, we pushed the miniaturization of electronics. That led to the microchip and to the computers you have at home. And that, of course, led to giant revolutions in technology. So I'm not smart enough to guess the future, to know what the next technological application is going to be. But this should not be a reason to stop the advancement of science, to stop dreaming, to stop imagining, because physics is imagination, and as such, it is one of the primary drives for innovation, and intrinsic, in fact, to the human spirit. Black holes, neutron stars, supernovae, mergers in spirals, ringdowns. The universe is telling her story, yelling her story out into the nothingness. Really, all we have to do is close our eyes and listen.